In this next example, I once again have a normal distribution with a mean of 0 and a standard deviation of 1, which makes it a standard normal distribution. I would like to calculate the probability that if I randomly pick a clock off the assembly line, that it is more than 1.64 seconds fast. What's the probability that a clock is this fast? Well, what are we talking about on here? If I know fast is over on this side, and if I put in my standard deviation markings, that's 1, 2, well, 1.64 as a boundary line is approximately probably right in here. So if I'm talking about the clocks that are more than 1.64 seconds fast, I'm talking about this area under the curve over here. Okay. How much area is that under the curve? What percent of the area have I shaded in red? Whatever percent I've shaded in red will be the probability. So once again, here's my boundary line. I first have to change my boundary line to a z-score, but we know that for the standard normal distribution, the z-score for 1.64 there is going to be 1.64, just whatever my x value is. This is the x-axis, recall. So, looking up 1.64 on this table, I'm now on the positive side, so I need to go to my positive z-score half of the table and look up 1.64. Once again, I find the whole number part in the tenths place over here at 1.6, and then bringing the table across to 0.4. Can we show all that at the same time? Maybe if I zoom out a little bit. Hopefully you can still read the numbers. Okay. Here's my 0.04 column. So the number is 0.9495. Hopefully you're following along with your own A-2 table and you can see this. But it's 0.9495. So I get 0.9495. Well, I don't know about you, but that sure doesn't look like almost 95% of the area. It looks like very little of the area under the curve. So what's going on here? Well, keep in mind that this table only shows you the area to the left of your boundary line, not to the right. So really, this 0.9495 is the area under the curve to the left. So how am I going to find how much is to the right? Well, aren't these complements? Doesn't the amount of area to the left plus the area to the right have to add up to 100% of the area, or 1? So all I really have to do when I'm talking about areas to the right of the curve, I've got to remember to do one final additional step and take 1 and subtract from that 0.9495. In this case, I'm going to get 0, 0. That's a 4. That's not a 0. That's a 5. And what have I got here? A 0. So my answer is, let me make it a little more readable, 0.0505. And I imagine you've noted by now that this table has probabilities accurate to 4 decimal places, and we're used to rounding them to either 3 decimal places or 3 significant digits. You always, when you go to do the homework, check to see exactly how the homework or the quizzes want you to answer the question. Do they want it rounded to 3 decimal places, 4 decimal places, or 3 significant digits? Always make sure you know how you're supposed to round it. So the probability that we get a clock that is 1.64 seconds fast is just a little bit more than 5% chance. All right? Next example. Once again, I highly recommend that as you're doing these problems yourself, you do just like I'm doing, draw a picture of the mathematical idea. That makes it so much easier to understand if you have a picture that you can look at. Once again, we're assuming I'm working at the clock factory as a quality control engineer, and we have a mean of 0 and a standard deviation of 1, both in seconds, in terms of whether the clocks are running fast or slow. All right, this time I want to know what's the probability that the clock, let's make this in complex here, the clock is between 1 and 1.75 seconds slow. What's the probability you randomly pick a clock off the assembly line and it's running between 1 second and 1 3/4 seconds slow? We can easily find that probability because this is a normal distribution and we have a whole table of values that have already been calculated for us by using calculus. We don't know calculus, but we do know how to use this table. All right. Here's what we have to do in this case. We draw the picture, put our boundary lines in place. If we go out to the left, since we're talking about the slow end, this is -1 and this is -2. So if I'm talking about between 1 and 1 3/4 seconds slow, my boundary line is right here at -1, and my other boundary line is right here at -1 3/4. So in terms of area under the curve, I'm talking about the area between these two boundary lines. Okay? So now how in the world am I supposed to figure out a probability with that? We know that the table only gives me the probabilities of areas under the curve from the left all the way over, not just part way over. Well, think about this. If I could find the area under the curve to the left of -1 all the way over, and if I then find the area under the curve to the left of -1 3/4 all the way over, if I subtract this area from this total area, won't I have this area that I want between these two boundaries? So once again, we're going to find this area from -1 to the left and subtract from that the area under the curve from -1 3/4 to the left. So let's do that. So my z-scores are, I have two of them. I have a -1. We'll find out what that is. And we want to write that as -1.00, always two decimal places. And my other z-score is going to be -1.75. Okay, using this table, we're back on the negative side. Let's see what it says. For -1, where are we? There's -1. There's -1.0, and our second digit is also 0, so that's 0.1587. Okay. 0.1587. That's how much of the area is to the left of -1. And let's find -1.75. All right, -1 0.7 is here, and taking it over, there's 0, 1, 2, 3, 4, 5, there it is. If you can read that, that is 0.0401, all right? 0.0401. And we said to find the area between the two boundary lines, I need to subtract these two areas. So if I subtract, I get 0.1186. So we can say, and I'll say it two different ways, the probability that we get a clock that's between 1 second and 1 3/4 of a second slow is 0.1186, or almost 12% chance. Another way of stating it is, we expect almost 12% of all the clocks that we make at this factory to be between 1 second and 1.75 seconds slow. Okay? I want to do one more example in the next video.